Hi folks, this video is extra practice placing sentences on this chart. We've said that first order logic includes the truth functional connectives and the quantifiers and the identity predicate, but it doesn't include any other predicates. You might be wondering, how exactly is it? Why do we know that it includes some things but not others? Let me show you. Remember, formal systems have three different parts. We've said they have a formal language, a semantics, and a proof theory. And we've talked quite a bit about the formal language in FOL. Well, the semantics and the proof theory are really where it gets totally specified that identity must mean identity, because all of the logical symbols, like the truth functional connectives and the quantifiers, are given special meanings in the semantics. And that's where we say identity has to mean identity. But any other atomic sentence can be possibly true and possibly false. Predicates can change their meaning from one occasion to another, one interpretation to another, but identity can never mean anything other than the way that we say we're going to use this symbol. And the semantics goes hand in hand with the proof theory. So all these symbols that get special logical meanings in the semantics also get their own proof rules. So, we're going to be able to do formal proofs using the identity predicate. You can't do the same sort of proofs using other predicates that aren't built into the system. So that's why this is how identity gets the special role. This exact same concept where some terms are built hardwired into the system exists in programming. So if you're familiar with any programming languages, oftentimes you can define some words to mean whatever you want. Like I can define message to just mean this, this little string of symbols, I love logic. But I cannot define the word print however I want. Print is like built into the language itself, where it always means something when the computer executes this code. And when I make identity, have some proof rules and have a certain semantics, this is basically like making it a keyword. I'm baking it into the system itself that identity has this special role. And it is the only predicate that gets this special kind of treatment. Okay, now I said we were going to get some practice. Here's a new sentence. Why don't you take this complex sentence with some quantifiers and see if you can figure out where it goes. So pause your videos now. Okay, that was your chance to pause your videos. This sentence is a logical truth, but it's not an FO validity. How do we know that? Notice if these predicates actually meant what we know they mean, if they had their intended interpretation, you could not possibly make this sentence false. This says something is smaller than A. So if that's the case, then it's not true that anything is larger than A. Well, if this means smaller than and this means larger than, then this is necessarily true. So this sentence is a logical truth. But first order logic doesn't know the meaning of the less than and greater than relations, or smaller or larger than relations. So if this had the intended interpretation, it would have to be true. So we know this is a logical truth. That's how the symbol works. But first order logic doesn't know these other predicates' meanings. It only knows identity's meaning. And so for all first order logic goes, this could just be any random binary predicate. And this could be some other random binary predicate. And on those other interpretations, the sentence would not come out as necessarily true. So that's why it doesn't count as a first order validity. Okay, thanks.